We are now live on YouTube. Say hi, everybody. Hi. Okay. I almost froze. Okay, that's not good. Okay, so today's topic is one of those important topics because some of the stuff can be difficult to understand. And I know for the 10% of you who are on Facebook right now, you're the ones the day before the exam are going to come to you. I don't understand. Explain it to me. No. So pay attention today. It's kind of important. It's not that difficult. It's conceptually it can be problematic because now we take that quantum leap from basic descriptive stuff you're used to in high school to doing stuff that's a little advanced. That Kahina's already introduced some of it in the lab, thank goodness. So it'll be entirely new. But let's go over what we did already. We've done the normal distribution already, probably to death. You're probably sick of the normal distribution, right? You know all about it now. It's this. It has certain characteristics, has standard deviation, and has a mean, and is symmetrical, and so forth. We talked about the Z distribution, and that, of course, is the normal distribution in which standard deviations represent Z scores. And we have some standard Z scores. We have that 3 sigma rule. And we looked at we didn't look at other distributions, but there are many other distributions. Today, we're going to look a little bit at a couple of other ones. We're going to learn about the T distribution, which forms a foundation for much of what we'll do for the rest of the semester. And we're going to hear about something called the binomial distribution that you don't need to know about. But recognize that they do exist. There's a Poisson distribution, there's a Gompertz function, there's all these endless distributions. So recognize that everything you know about normal distribution is not the end of statistics, even though some classes pretend that it is. But the normal distribution is the foundation for everything pretty much that you'll need to know if you don't become a professional statistician. But the T distribution is a derivation of a normal distribution that we're going to learn about, and keep them separate in your minds because they're quite similar, but they have one important distinction. Now, like I said, statisticians love the distributions. Don't let it get you down. So remember, inference is when we do things to a sample to learn about the population. What do we call things that we measure in the sample? What's that word? Yeah. Statistic, exactly. What do we call things we infer about in the population? Parameter, precisely. I keep on repeating that because it's important. Keep them separate in your minds because we're using statistics to measure parameters. Oftentimes, I'm going to show you formulas involving parameters, but we don't know the parameters. So we use the statistic in our sample and plug that number into the formula to estimate our parameter. That's why we keep them separate all the time. Last time we talked about the null hypothesis versus the alternate hypothesis. The null is H sub naught, and the null essentially says nothing's going on. If I'm comparing two groups, are they different? The answer is always no. The null says no, they're not different. Or is this finding significant? The answer is always no. The null says no. So in science, our default state is always nothing's happening. Science is conservative. The alternative hypothesis, we either write as H sub A or H sub 1, says the opposite. Something's going on. So we can reject the null. We never accept the null. Do you remember why? Yeah, that's Mateo. Mateo, yeah? Okay.
You can't accept the null because, I mean, you can't for sure accept something.
I can sense in your mind that you know what you're talking about. Yes. It's essentially because we don't have positive proof that nothing's going on. We just haven't got enough evidence to say that nothing's going on. So reject the null, or we fail to reject the null. It's hard to prove innocence. Okay, so speaking of innocence and guilt, we have two types of errors that we talked about, type 1 and type 2. Using the courtroom analogy, type 1 error is when we convict an innocent person or incorrectly reject the null. In the case of a drug trial, that would be saying a drug works when it really doesn't work. And type 2 error is when we acquit a guilty person, or we incorrectly fail to reject the null. Something's going on, we didn't find it. So the drug actually does work, but we don't think that it does. Okay, keep those straight in your head. And we have a notation for them. It's alpha, and this is beta. We don't care that much about beta in this class. We focus a lot on alpha, though, type 1 error. So the level of type 1 error that we accept in any analysis dictates the amount of precision in our guesstimate over whether or not something is significant or not. Yes?
If the drug does work, how would you think that it doesn't? Like, if it does
All right, I have two groups, 1,000 people here, 1,000 people here. I give them both, give this group the drug and that group doesn't get the drug. Out of this 1,000, one person gets better. Out of that 1,000, nobody gets better. Does the drug work? Doesn't? I don't know. One person to work for. The point is, when large numbers, we're dealing with averages and trends. Oftentimes, there are anomalies. So statistics is all about identifying the anomalies versus the actual trend. In any given experiment, something's going to happen that has nothing to do with the experiment. You're going to get better all by yourself. It has nothing to do with the drug. So we never know if the drug actually works. So we talk about truth. This is truth. Actually does work. Actually doesn't work. We never know. We never know if the man's actually innocent or if he's actually guilty. We just never know. So our inability to measure truth is the error. We try to make the error as small as possible. It's kind of like smoking and lung cancer. It's possible to get lung cancer without smoking. It's possible to smoke and not get lung cancer. So I have two groups of a smoker and a non-smoker. I'm going to get some people in both groups who get lung cancer and who don't. So what we deal with are averages all the time. So we never know if it actually does work or not. We just know, on average, what happens. Okay, so directionality. This is two-tailed and one-tailed stuff. So if we want to know if one thing is bigger than another, or if this drug makes you better than that drug, that has direction associated with it. If we don't care if it makes it better or worse, just that it's different, that has no direction to it. So if we don't care about direction, we call that a two-tailed test. That's when we look at either end of a normal distribution of possible outcomes, whether it's extremely more than the average or extremely less than the average, two-tailed. If it's one-tailed, we care about if it's extremely more than the average, or in some cases, extremely less than the average. So it's almost never one-tailed, except in exercises that we do in class. Right? So, because in real life, we care about just different. We don't care about if it's more versus less. Right? So now the new stuff. So we're kind of clear on that, I hope. Yeah? Good. The new stuff begins with the old stuff. I mentioned that a normal distribution is essentially a probability distribution function. And don't get freaked out by the math terms there. All it means is the area under the curve represents the probability that something happens, because that's the number of times I've seen it. So probability, as we explored, is the number of times something happens divided by the number of times it could happen. So a normal distribution represents the number of times something happens divided by the number of total times it could happen. So that's what's happening here. So let's look at a distribution of IQ scores. And IQ is a fascinating example because IQ scores are always transformed such that the mean is 100. Right? Every year we modify it, the mean is 100. So it's a good one to do statistics on. So let's say we have a distribution of IQ scores for 10,000 10-year-old kids, and we know the parameter is 100 because IQ scores, the parameter is always 100. And the population standard deviation in this case is 15. How do we know this? Because we did a census, let's say, of all these people over here. Okay, so if you get an individual child who has an IQ score of 130, then that represents 2 z-scores above the mean. Remember that? Because the z-score represents the number of standard deviations. What's a standard deviation? Do you remember? What's a deviation? It's important stuff. We got to make the foundation. Yes, ma'am. Exactly, a difference from the mean. So a difference between an individual score and the mean score. So standard deviation is kind of like the average deviation, but we compute it differently, do you remember? So the number of standard deviations is our z-score. So the case of a score of 130, happens to be over here, you're exactly 2 standard deviations above the mean. We know from the z-score calculator that that's about 2.3% of the top of the entire distribution here. So 2% of the upper end. Great. So that means that this person of 130 is doing better than about 97.7% of everybody else. But there are 2.3% of people who are better than that person. Okay. So because it's 2.3, we say there's a probability of 0.023 of randomly selecting a child with an IQ that's higher. If I was to reach in this pot and pick someone randomly, chances are I'm going to get it from this pile, not from that pile. So the probability of getting it from this pile is 0.023. So my p-value is 0.023 of getting something more extreme than my current value. All right? Still with me? Excellent. So we start using this terminology now, P. P will come up again, again, and again. P is the foundation, one of the many foundations of the kinds of stats you will read about in studies and so forth. Okay, so we know that the distribution of IQ scores in the general population is this. The mean is 100, standard deviation is 15. We know that. So we take a random selection of 25 kids, some school in Ottawa, and we measure their IQs. Okay. If we sample 25 kids, is their mean score going to be 100? What do you think? Probably. What's it going to be? Yes or no? 100? Probably not. Why not? We know the universe mean score is 100, but these 25 kids won't be exactly 100. Yes? Other factors influencing, sure. Or the thing is, let's say I'm trying to decide, I know the average age of university second-year students is 21, and I take your average age, because you're a sample of second-year students. Am I going to get exactly 21? I'm going to get maybe 21.2, maybe 19.8, because they're individual variation, right? There's always errors in each sample, okay? So each sample is a little bit different from every other sample. We call that variability. Each sample of second-year students is different from every other sample. Each sample of 25 10-year-old students will have a slightly different IQ set than another sample. So in stats, we're always dealing with averages, typicalness. Right? So sample means tend to fluctuate from one sample to another. We call that sampling error. It isn't really an error. We didn't make any mistakes here. An error just means it's different from the mean. So the terminology you can be using sometimes. So again, because of sampling error, the different samples that I choose of my 10-year-old students will have different mean IQs. And they'll be different from this parameter of 100. So it might be 98.2 or this or that, whatever. Rarely is a sample mean exactly the same as a parameter mean. It can happen, but rarely is that the case. Okay, so if we're going to collect 100 random samples of 25 kids, 100 little pockets of samples, and I get the mean IQ from all of them, each one is going to be a little bit different from each other. They're probably going to be around 100, but they're going to be a little bit different. So, like I said, they're going to be around 100. Some will be a little less than 100, some will be a little more than 100, but they'll be clustering around 100 because that's what the overall mean is. If we were to collect an infinite number of samples of 25 10-year-old kids and computed the mean IQ for this infinite number, and I plotted the mean IQ of the infinite number on a graph, you know, how many of my samples had 0 IQ, how many samples had 5, how many had 100, how many had 120, how many had 200, what would that curve look like? It would be the normal distribution. That's the magic of normal distribution, like that. So taking a sample from each of these, compute the mean, and the average of all these averages is going to be magically 100. You got to trust me on that. That's the magic of what we call the central limit theorem, is that it doesn't matter what the individual samples are. If I take an infinite number of samples and I take their average, that average is the same as a total average. Okay? So the graph of the means of all our infinite samples would look like a normal curve, and the mean is going to be my parameter. Okay, how does that help us? We'll see, hopefully. So they have something called the sampling distribution of the mean, and that's the distribution of the infinite number of sample means. Whew, there's a lot of words to remember here. So the sampling distribution of the mean is just that normal distribution. If I take a mean IQ from my infinite number of samples and I distribute them, that's my sampling distribution of my means. Some of your faces are like, what? We talk about what? So I'll say it again, even though half of you have it already. If I take my infinite number of samples, and I get a mean IQ from each of those, and I plot the frequency distribution of all those means, that is the sampling distribution of my means. In other words, the distribution of the means of all my samples. And it's always normally shaped. It's always a bell curve. This is a theoretical distribution. It doesn't exist. It can't exist. I can't take an infinite number of samples. Obviously, it's not possible. If I can get close, I can get like 1,000 samples or 10,000. I had $1 billion to spend. I just can't do infinite. Therefore, it's always theoretical. It's never real. But we're a big fan of our theoretical samples. We use our theoretical samples here, distributions, to make all kinds of fancy maths. So again, the central limit theorem that we covered a few lectures ago says just this. It says that the mean of this magical sampling distribution is in fact going to be my parameter. Now, the larger my sample size is, the more normal they become. So suddenly the number of people in my sample, the more that my sampling distribution begins to resemble my normal if I have less than an infinite number of samples. So large n's, large numbers, help me. It gets me closer to this magical shape of a Gaussian distribution. So that takes us to a new idea. That's the standard error of the mean. Whew, a lot of words sound the same, right? So sampling distribution of the mean is different from the standard error of the mean. The standard error of the mean is the SEM. This is the standard deviation in my magical theoretical distribution. All right, I'll go back and say that again. So remember that if I take my infinite number of samples, and I take a mean from each of my infinite number of samples, and I do a frequency distribution of all those means, I get this magical theoretical bell curve that I call the sampling distribution of the mean. And every bell curve, as you know, has a standard deviation associated with it, a measurement of variability of width. So the measurement of variability of width of my magical sampling distribution of the mean is this thing that I call the SEM, the standard error of the mean. Okay, that's all it is. It's just the standard deviation in this theoretical curve, right? Okay, don't say no yet. Good. So I presume you're with me. So we have an infinite number of samples. Each sample has 25 students. We take the mean of each sample. We plot them and get my normal curve, right? It's normal. And so we define the SEM as the standard deviation of this new curve. Nice. Okay. So the larger my SEM, the less likely that my sample mean is a good estimate of the population mean. What the hell does that mean? It means that this magical distribution that I talked about, the theoretical one, the SEM that I compute is a measurement of its width, right? Because that's a standard deviation. It's a measurement of variability of width. So the larger it is, the more error there is in my ability to select a random sample and have that random sample have a mean close to the mean of my magical distribution. So in other words, I want the standard deviation, the SEM, of my theoretical curve to be as small as possible. The smaller it is, the more likely than when I choose one sample, the mean of that sample will represent the parameter in this magical sample. Whew, that's a lot of theoretical stuff, right? Still with me? Good, cool. Some people are frowning at me. All right, I'm a little nervous. Okay, good. Still with me. Let's see if it comes through in a second. The actual SEMs are never known. Why is the SEM never actually known? Yes. Exactly. It's a characteristic of a theoretical curve that doesn't exist. So I can never truly know what it is, but I can estimate it. Because remember what I said earlier. Our sample statistics are just estimates of our population parameter. This is a population parameter. I can use characteristics from my sample to estimate this. And that will tell me how close my mean in my sample of 25 kids is to the theoretical true mean in the general population. Okay. What do we need in order to estimate the SEM for a real distribution? We need to know the mean in my sample. We need to know the SCD. And we need to know the number of people in my sample. I have all that. I got 25 kids. I compute the mean IQ for all of them. And I know the standard deviation in my sample because I know how to compute that. 25 kids, add up their IQs, divide by whatever, I have it. So this is information I have in my sample already. And this formula allows me now to estimate the SEM for this magical theoretical distribution from characteristics of my sample. So again, N is the number of people in my sample. That's 25 kids. Standard deviation is the width in my sample. We know how to compute that. So this now tells me the theoretical distribution that theoretically my sample was taken from, this magical universe of IQs, has a width of that. Okay, that sounds really magical and weird and really philosophically constructed, I know. If you don't get it, it doesn't really matter, as long as you can do the math. Right? I would like you to be able to get the concept as well, because that helps you navigate through this process and recognize that when we're doing frequent statistics, all we're doing is testing to see if my sample came from this magical universe with this distribution. Right? So the statistical test that I do tells me if this sample came from that universe or not. Because my null hypothesis says, yes, it did come from that universe. And if I reject my null, what I'm saying is, oh no, my sample came from a different universe. A universe in which the man is not guilty, or a universe in which IQ is not 100. That's essentially what statistical testing is. It's saying the evidence for me does not represent the assumed theoretical universe in which my defendant is guilty. That's pretty deep. I gotta write that down. That's good. Okay, let's back up a second. So this is my formula. I said I can never know what the SEM is because the real SEM is standard deviation of a theoretical construct. So we are estimating our SEM from our existing stuff. So look at this formula now. The larger my n, the smaller or larger my SEM becomes. Does it go higher or lower? If the n goes up, does the SEM go up or down? It goes down. This goes smaller the more n I have. That's good. I want a small SEM. I want small standard error. Right? So that tells me right now that for every study that I do, I want as many n's as I can get. Sample size is critical for everything that we do. And this is the reason, because sample size reduces the error in my estimate and allows me to better determine if my sample came from the universe in which IQs are 100 versus it came from the universe in which IQs are not 100. Right. We always like to have a high MM, and in order to have a low SEM. And why do we want a low SEM? Because SEM is all about precision in my attempt. Okay, so here is again my distribution of IQ in the world for 10-year-old kids. All right, so that's how it's distributed. We have taken a sample of 25 kids. In our sample, let's say the mean IQ for my 25 kids is 101. Right? Now, if you didn't know statistics, and I ask you, is that different from 100? You say, of course it's different. It's one different. Are you stupid? It's different. I don't know. How do we know it's different from 100? But no, because we know statistics, we know that there's some error in that estimate, and we have to establish whether or not that error allows me to accurately say that the mean of my sample is statistically equivalent to 100 or not. And when I say it is statistically equivalent to 100, again, what I mean is my sample came from the universe in which IQs are 100. And if I say that my sample mean is not statistically equivalent to 100, what I'm saying is my sample came from a different universe in which IQ means is not 100. Right, and we're going to test that supposition right now. So in my sample, I have an SD, a standard deviation of 10.5. How did I get that? I did the math. You know how to do that. If I give you a bunch of 25 IQs, you know how to compute a mean and a standard deviation. We did that in the first couple of weeks. So let's say, here's our data again. My mean is 101, my standard deviation is 10.5, I got 25 kids. The SEM then is going to be my standard deviation divided by the square root of 25, or 2.1. So this is the width of this theoretical distribution that I hope my sample came from. Keep in mind now, if my sample was larger, or were larger, grammatically it's were larger, right? If my sample were larger, 225 versus 25, my SEM would be much smaller, so it would be 10.5 divided by the square root of 225 or 0.7, that difference. So clearly, a larger sample gives me a more accurate estimate of whether or not my sample came from this magical universe. All right, so put that away for a second. So again, our sample, we have a bunch of kids, 25 kids. Their mean IQ is 101. The SEM I've computed now is 2.1. You're all clear on how I did that. Okay, what does that mean? Okay, why do I compute a sample mean to begin with? I compute a sample mean to begin with in order to estimate a parameter mean. That's my goal here. Okay. So now we can look at our z-scores. All right. So imagine we have a normal distribution with our sample mean is 101 and our SEM of 2.1. Now we want to know with 95% confidence whether or not this is a true or an accurate estimate of the actual population mean. Again, I don't know what the actual population mean is. I want to know if this 101 is a good estimate of it. I have set my type 1 error here as 0.05. Type 1 error I can set to be whatever I want. How much ability or accuracy in my jury do I want? I want it as tight as possible, obviously, but I make it as tight as possible that I run the risk of letting some things slip through my fingers. So 0.05 tends to be the standard. 0.01 is the other standard. If you read papers and what they said to other members, be wary. Good scientists tend not to do that. 0.05 or 0.01. And 0.05 means I'm going to estimate now my IQ within a 95% confidence, because 0.05 is 5% error, the remaining non-error is 95%. How does that look? So again, that's my sample. Right? What z-score corresponds to a 95% chance of getting a mu close to an m? Remember your z distribution? What z corresponds to 95%? Remember my 3 sigma rule? It's around 2, if you remember correctly. So 2, a z-score of 2 gives 95% more or less under the curve. Yeah? The exact number is 1.96. So 1.96 keeps popping up a lot because 1.96 represents 2 standard deviations beneath any normal distribution, and that also represents 95% of all my responses. Okay, 2 what? 2 standard deviations. So standard deviation in this situation is what? It's my SEM. It's my standard error of the mean. Why? Because I'm trying to model this theoretical distribution. A lot of stuff going on. Okay. In other words, the probability is 95% that all the sample IQ means from the population of children would be no more than 2 standard deviations above or below 101. Okay, so 101 is the mean that I have. I have got no other means. I just got my sample. That's what I got to work with. And I got to figure out every possible mean is likely to be above or below a certain range. And I've computed that range to be 2 standard deviations above or below. And that standard deviation is 0.7. So 2 standard deviations is 1.4. 1.4 below 101 is 96.8. 1.4 above 101 is 105.2. Yeah, that's not right. Oh, sorry. Yeah, sorry. It's just 2.1. 2.1. Standard deviation is 2.1 over here. Okay. So 2.1 times 2 is 2.4. 2.4 below 101 is 96.8. 2.4 above 101 is 105.2. 4.2. Barely awake. 2.1 times 2 is 4.2. 4.2. 4.2 above below this. Sorry. Now, if my sample size were larger, remember 225, my SEM goes down to 0.7, and so the range goes from 99.6 to 102.4. As you can see, in the middle between these 2 ranges is always 101. That's my sample mean. I'm getting a tighter and tighter estimate where the likely mean actually is. Okay? And the more tight I get, the closer I get to my truth. So a larger sample size means a greater precision in estimating the population mean. Okay. We could have done the same thing with a 99% confidence range. I would have done this by looking up a z-score that corresponds to 99, and that would have been 2.33. So 2.33 standard deviations above and below my sample mean would have been the range in which 99% of the time my population mean would be in that range. So I'll say that again. 2 standard deviations above and below represents the percentage related to my alpha. In this case, it's 99%. So 99% times the sample that I've chosen randomly from this universal sample would be within this range. That's essentially what it's saying. Okay. Back up a second, and this hopefully will be clear when we do an example. There are 2 basic approaches here. We talked about parameter estimation, and we talked about hypothesis testing. Last time, we did hypothesis testing. We had a null hypothesis and an alternative hypothesis. And we tested the hypothesis using our z-scores and stuff. Now we're doing parameter estimation. I just estimated the mean IQ of 10-year-old kids. And I'm trying to compute now an interval in which it is likely to be the truth. Right? So I'm confident this amount that my estimate is actually the truth. That's different from what we did last time when I said I'm going to reject the null or accept the null. This is a common approach. Right? We did hypothesis last week, but what we did today is actually what the medical community and the scientific community tends to like, because this allows us to report an actual interval of confidence that we call the confidence interval. And I think Kahina has introduced this in the lab already, which is good. So it's not entirely new to you. So what we carry is, again, what is the range in which I am 95 or 99% confident that my answer represents the truth. And the truth is the mean in this magical universe of IQs. Okay, so parameter estimation is when we estimate population value, and we have a point and an interval. The point is my mean, and the interval is the width of that. So here it is. The mean age of university students is 21 years, and that's my range, from 18 to 21.5. Let's say that's my 95% confidence interval. So I am 95% confident that the actual age is between here somewhere. This is what my sample tells me. This is what the actual parameter probably is. It's in this range in here. So that's the actual point estimate, and this is the confidence interval. Note that I call this parameter because, again, my statistic is used to estimate, to emulate a parameter. So if I could do the same math on you guys. Take all your average ages, calculate the standard deviation, and compute what this range is going to be. And I can get your mean age would be my estimate of the parameter, and this is how confident I am that your mean age truly represents the mean age of the university. Okay, I'm not sure if you're good. I'm all scared here. So, okay, skip that. It's pretty obvious. The interval is the hard part here. The interval is the range of values in which the parameter probably lies within a certain amount of confidence. It could be wrong. If I say 95% confidence, that means I'm 95% confident it's in that range. There's a 5% chance it's not in that range. There's a 5% chance I'm entirely wrong. Right? So that's why we like to have a high number for my confidence. So 95% confidence represents an alpha of 0.05. So type 1 error. Did I do this in error? Did I find an effect in error? I have a 5% chance that it was erroneous. So we're talking here about confidence intervals. The example we did involves z-scores. In reality, we don't use z-scores. We use something else. And from now on, you're going to be using something else called a t-score. I use the z because you understand z's. Now we're going to go and look at how it looks in the real world. So a confidence interval, a 95% confidence interval, is the range of values in which the true parameter probably lies 95% of the time. Okay. So to compute a confidence interval, we need to compute confidence limits, as we just did. And the most common ones are 95% and 99%. That corresponds to an alpha of 0.05, and this corresponds to an alpha of 0.01. It's almost never anything other than these two. Again, if you find something that's not one of these two, be skeptical of the science of what you're reading about. It's almost always this one. This is pretty rare too. It's really good science that has this. Usually we rely on 5%. So here's a formula for computing a confidence interval. And again, if you've understood nothing that I've done up to this point, it doesn't matter because all the computations really from this point on, and you can still do the math and be fine with Mark and all that stuff. So what you need is your sample mean, which is what you compute from your sample. What you need is the estimate of your SEM that you know now, because that's just your standard deviation divided by the square root of the number of people in your sample. And you need the value corresponding to the area underneath this theoretical curve that corresponds to the alpha value that you want. What the hell does that mean? So that means that either a z-score or something else, something you got to look up. You mean your SEM is something you have to look up from a theoretical distribution. So when we're talking about confidence intervals for means, we care about the t-distribution, and we're going to look up a characteristic of the t-distribution. What the hell is a t-distribution? T-distribution is a lot like the normal distribution. It is essentially the normal distribution. It's bell-shaped, symmetrical. If you were to look at it, you'd think, it's exactly the same thing. Right? As the sample size gets high, the t is pretty much identical to the normal distribution, which we also call the z-distribution. As the the sample size gets small, rather, it flattens out, right? And so tails get fat, and the top part gets platycritic. Remember that word? It's flatten. Okay. So here we go. DF stands for degrees of freedom. We will revisit degrees of freedom in the second half of this class. The degrees of freedom is a philosophical construct. I won't go into what it means except to say it just measures the number of people in your sample. Computationally, degrees of freedom is number of people in your sample minus 1 if you've got one sample. Okay, so when you see degrees of freedom, just think of it as a sample size. So here we have, for one person, or like in your sample, this is what t-distribution looks like as it goes. No, here. So this is one person, this is two, it's higher. So the more people you get, the more tight and high the t-distribution looks until it resembles exactly a z-distribution. Right, so the more people you have, the more flat it becomes. It's also called a student's t-distribution. For me as a student, it has nothing to do with students. It's called a student distribution for an interesting historical reason. So it's a precursor to the t-test, which is one of the foundational tests that you will learn about probably next week. If you can do a test, you can do probably half of all math done by most common, half of all statistics done by most common biological tests, because biological statistical tests aren't very complicated. The t-test is a standard test for comparing two different means. We'll do the t-test next week. But the t-test is also called the student's t-test because it comes from student's t-distribution. It has nothing to do with students. It has to do with this guy, William C. Gossett. He used to work for the Guinness Beer Company. And he developed a method of comparing whether or not the average beer quality between vats was the same. And he called that the t-test. Now, he was afraid of publishing under his own name because he didn't want his employer to know that he was doing stats on the side and make, whatever. So he called himself student, which has confused people for generations. It has nothing to do with students. It's because this guy called himself student. And so it's student's t-test. He's actually William Gossett. That's him. That's a prototypical nerd. Look at him. That's great. Okay. So this is, again, showing what the t-distribution looks like. So this is the typical z-distribution. The z-distribution is the same as the normal. It's the same as the Gaussian. Same, so many names to it, right? So we see z-distribution. It's just everything we've looked at so far. Okay. This is t when the sample size is about 30. This is the t when the sample size is much smaller than 30. Notice that the more people we get, the more identical it looks like the z-distribution. Essentially the same as a normal, except that its flatness varies with sample size. That's the only distinction, really. The regular z, its flatness varies with standard deviation. Okay. So remember we computed our confidence interval just now. We wanted that n to be involved. Important for us to have a measurement of n because n gave us our standard error of the mean from our standard deviation. Our z-distribution doesn't have an n built into it. It just has a basic SD built into it. So we use a t-distribution because it has an n built in. It allows us to have flexibility with respect to the number of people in our sample, because the number of people in our sample determines the accuracy of our estimate. So here we go. We say that it varies with the degree of freedom, and the degrees of freedom is just n minus 1. It's a lot, I know. But it's important to know that right now because the second half of this class, we'll be doing a lot of work with degrees of freedom when we do things with ANOVAs and other kind of multivariate methods. So I'll say it again for like the 8th time. The t-distribution is almost identical to the z or the normal distribution, except that it likes to have lots of people in it. More people, better. All right, so back to our example. Here we have a sample of 225 children, not 25, but 225. And the IQ is 101. What's the SEM? It's going to be just like that time, standard deviation divided by root n. So it's 0.7. Computed that already. So that's our data. What can I do with this? I'm going to compute a 95% confidence interval using this information. So the formula for the 95% confidence interval is this. Here is my statistic, my sample mean, plus or minus a particular value from the t-distribution multiplied by the standard error of the mean. All right? Standard of the mean we just computed. My statistic, I know from my sample. It's this that I'm lacking. So how do I get that? I get that from looking it up in the back of the book or from using an online calculator. Page 412 of your textbook, there's a table there. What you need to look up in the table is you need to find the level of confidence you're looking for and your degrees of freedom. This is where it comes in. So the level of confidence you're looking for is the type 1 error. So depending on how the table is set up, it's going to ask for either the alpha value, which is your type 1 error, or the confidence level. Your confidence level is 95% if your alpha is 0.05. I think your table is set up in terms of alphas. Right? So here, 95% or alpha equals 0.05. N minus 1 is degrees of freedom. In this case, it's 225 minus 1. 224. With this information, I go to the back of the book and I look up the corresponding t-value. This tells me the number of t's into my distribution that correspond to 95% confidence that my statistic is close to the parameter. Ha, that's a lot of words. Look at that. If I look it up, I get 1.96. Well, that sounds familiar, doesn't it? That's exactly the same as my z value. Why'd I go through all this nonsense if I could have gotten exactly the same thing? Why is this, the t-value, the same as the z value I looked up earlier? It's a different distribution. Any ideas? Yes? No. But good for you, brave, to posit a guess. Yes, sir. Exactly. It says that I'm close to the z distribution. Is that what you meant? I'm sorry, I misunderstood. It's close to the z because the sample size is high. Right? So, like I said, it's over 30. You're going to be pretty close to it. So you may ask yourself, then why do we care about the t? Because we do care about these slight nuances. It makes a difference with other kinds of computations. Right. So, not to belabor the point. So here we have my data again. My sample, the number of keys I have, and standard error. And there's my formula. And I plug it in, and I got 1.96 times 0.7. That goes there. That goes here. I do the math, and I figure that, in fact, that times that gives you 1.37. And if I subtract 1.37 from 101, I get this. If I add it, I get that. So this is my 95% confidence interval for my sample of IQ students. What does that tell me? Anyone know? You want to guess? What does that tell me? Yes, ma'am? Yes, exactly. So there's a 95% chance that the actual mean is between these two. This is my sample mean. The parameter probably falls between this range here. That's what it tells me. Okay. So it's a lot like doing hypothesis testing, right? Where I hypothesize that the null hypothesis would be my sample mean is the same as 100. And I do all the math, and I either reject or accept that, or to reject my null hypothesis. This has a little more elegance to it. It allows me to see how much I'm off. Okay. Okay. Could I have made this a 99% confidence interval instead? Absolutely, I could have. What I have to do then is look up a different t-value for 99%. And that would have been 0.58. And you can try that at home if you want. In fact, you don't have to because I just did it. So if I'd ask the question, is the mean IQ of children equal to 120? Which is a stupid thing to ask, but let's ask that. Right? From my sample, I get this confidence interval, and I conclude, no, the mean IQ of children is not statistically equal to 120 because 120 is not in that range. If I'd ask, is the mean IQ equal to 100.5, I could have said, yeah, it's in that range. Oh, yes?
But there is like a 5% chance that it's 120.
Exactly. 5% chance it's not in that range. It's not the same as saying 5% chance is 120. See, it's a distance there. Okay. Exactly. So this is for means. We did it for means. So we have a point estimate and we have an interval estimate. Notice there's symmetry here. That my point estimate is exactly at the center of my confidence interval. That's very convenient. It's not always the case. We just use a t-distribution to construct a confidence interval around a mean. That's standard. If it's a mean, we use a t-distribution. If it's something that's not a mean, like a ratio, odds ratio, or relative risk, or a percentage, we use something else. And the math for that is really kind of crazy, and I don't want you to do that. So we use a binomial distribution to compute a confidence interval around a relative risk or an odds ratio. So if you do this with BSS, it'll give you a crazy number for relative risk because they're using a complicated distribution. You're not going to do that because why freak you out for a stats class? All right. So the confidence intervals around proportions and ratios are not symmetric. You can have a range like this for your confidence interval, and your point estimate is over here somewhere. That's the nature of the math. So here's an example of these are confidence intervals of what? These are the percent female participants in nursing studies by age group. Right. So this is a typical way of representing data and studies, and this allows us to say, here's one group, another group, another group, and this is the 5% confidence intervals. I can now draw a line to see is there a value that overlaps all of them. So they all kind of agree around here. So if I choose this one, I get 2. If I choose a line over here, I get 2. So the truth is probably around here somewhere. Okay. So we see exactly how much error different studies or estimates represent. So I'll give an example of how to do this in real life. A study was done on a large group of people exposed to sulfates to find relationships between a variety of population characteristics and the risk of dying. So these are the actual data. So this is relative risk data. So this shows for each of these things that are associated with risk of death, here's a relative risk that we learned about a couple weeks ago. And this is a confidence interval for the true value of the relative risk. Now, remember with relative risk and odds ratio, what's the magic number that we care about? All kinds of ratios. You said, you mouthed it. What is it? What you said? What is it? You mouthed it? 1, exactly. Okay, so all ratios, the magic number is 1 because you're dividing something by itself. If it's 1, nothing's happening. So relative risks and odds ratios, we care if it's 1 or if it's not 1. If it's less than 1, it's protective. If it's more than 1, it's probably associative. So the way to read these things is to look at, does 1 appear in the range of any of these things? Does 1 appear in here somewhere? No. Nowhere in that range is there 1, meaning the unity, 1.00. In here, is there 1? Yes, there is. Dun, dun, dun. So we know that right there. There's probably nothing happening here. Even though my relative risk is 1.02, statistically, it's really 1. 1's in there. So we know that, hey, there's nothing happening here. Next one down, is 1 in here? Yes, it is. There's 1 in that range. So dun, dun, dun. We know statistically there's probably nothing happening here. Next one down, nope. This one, well, yeah, there's 1 right there. Dun, dun, dun. Take that one out. That leaves me with these 1, 2, 3 characteristics here that seem to be statistically significant in terms of an association with mortality. So that's a quick way to read these kinds of tables if it's a relative risk odds ratio, which it often is. If it's a mean, no. Look at something else. So your homework, you have 2 slides of homework here. You're going to construct a 95% and 99% confidence interval for these data. The answer they should be in the comments in the slide. I take them out. If the answer is not there, I'll post them later. And that too. Cool. You all paid attention so well.